Hi, I'm Guan Wang from Peking University. Here I'm going to share with you our paper accepted by CVPR 2024 OED towards one-stage end-to-end dynamic scene graph generation. This is a joint work with Zhimin, Qingchao, and Yang. For an overview, our paper addresses the problem of dynamic scene graph generation, DSGG, which aims to understand video and generates a sequence of comprehensive and structural representations, frame-level scene graphs, for given video. Scene graph consists of nodes for localized objects and edges for relationships between objects. Temporal context is essential to correctly detect objects and perceive their relationships at each frame. Because the objects are moving across frames and some relationships are dependent on adjacent frames. If only a single frame is available, we can now tell this person is sweeping the floor or just holding a broom. Existing works have largely adopted multi-stage pipelines for DSGG, which may include object detection, pair enumeration based on detection results, and so on. And recent works introduced object trajectory to aggregate important and long-term temporal context. However, multi-stage frameworks result in suboptimal solutions due to independent optimization. There are huge computational redundancy in pair enumeration, because its complexity is O n squared, where n represents the average number of detection results. Besides, complex scenes tend to yield inaccurate object trajectories, which will lead to error accumulation. To solve the issues of existing works, we propose the first one-stage end-to-end framework for DSGG in the way of set prediction. Besides, we introduced the progressively refined temporal interaction module to aggregate temporal context, which has no need of trajectory to mitigate error accumulation. PRM could improve the detection results of target frame based on reference frames, instead of trajectory interruption due to missing detection. Here is the overview of our method OED. OED consists of spatial context aggregation module and temporal context aggregation module. SA module is to extract spatial feature of relational pairs. TA module further obtains temporal context from reference frames. Let's jump into SA module. In SA module, we use a set of learnable queries to obtain corresponding relational pair features. Considering that predicate classification has large dependency on pair detection. For example, overlapping person and cup tend to correspond to holding or drinking from. We use cascade coders to pairwise instance and relation features. Besides, it is hard to obtain complete and correct annotations because the relationships are dense and temporally dependent. Therefore, we adopt matched loss to mitigate the negative effect of incomplete annotations, which is common in existing dynamic scene graph generation benchmark. Only the predictions matched with ground truth are used to calculate predicate classification loss, rather than deeming all unmatched predictions should be background. To further obtain temporal context, we first concatenate these decomposed features into complete ones. The pairwise features can directly interact with each other between target frame and reference frames. However, if all reference frames are selected, there are a lot of background noise introduced. Just using threshold to filter out features will miss some clues. In order to hit a good balance between noise and temporal context, we introduced the PRM module for temporal interaction in a multi-step way. In each step, only top K reference features are selected and interact with target features, while the K decreases continually to refine the noise. We evaluate our method on Action Genome dataset. It consists of 10,000 videos and 17,000 annotations, encompassing 35 kinds of objects and 25 kinds of relationships. We show the performance comparison under two settings. SGDT corresponds to the DSGG task itself, while predicate CLS assumes object trajectories are given, which is greatly beneficial for those trajectory-based methods. However, we still achieve certain performance on the SGDT setting and comparable performance on the predicate CLS setting. Here we present ablation experiments. We show the effectiveness of two modules and all designs in each module respectively. Then we visualize the attention maps of cascaded decoders and found out pairwise instant decoder attends more on subject and object areas, namely pair instance areas. The pairwise relation decoder pays more attention on contacting area, namely pair relation areas. This result corresponds to our initial motivation. In this paper, we propose a one-stage end-to-end framework OED with temporal context aggregation model PRM, which achieves superior performance. That's all my sharing. For more detailed information, please refer to our paper. Thanks for your attention.